Good morning, everyone. Okay, like today we will start a new chapter. Actually, we have already finished three chapters. The first, the 14, 15, and 16. And firstly, we talk about simple harmonics motion, and those simple we can see many real world examples for they move in simple harmonic motion. And you can see those simple harmonic motion can be represented as a sinusoidal form. Yeah, their movement can be represented as a sinusoidal move. And after we learn something about the simple harmonic motion, we know how to represent a simple harmonic motion with those sinusoidal form equations, and we also know most simple harmonic motion can be considered as a spring move, or like a pendulum move. And you can see string and pendulum, they have some specific feature, and you can use the equations to calculate the spring constant and to calculate the pendulum length. Yeah, so this is what we learned in chapter 14. And after that, we learn the traveling wave. You can see the traveling wave, uh, actually they have some specific character for all the traveling moves, traveling waves. And in the chapter 15, we learn some general mode for the traveling waves. And you can see we learn how to represent what's the relationship between wavelengths and frequency and velocity, and how the wavelengths what kind of the wavelengths can be divided to different kinds of waves, the transverse waves and longitudinal longitudinal wave. Yeah, and also the waves can be based on if they through if they can be spread we using through the medium or not. Like we can divide it the traveling wave as the mechanical wave or the electromagnetic wave. Yeah, and the mechanical wave, they will be transferred, they will be spread through the medium, such as a water wave, such as a stream wave, and the electromagnetic wave, and they will spread out without a medium, they will not based on the medium to spread out, such as a light wave and some radio wave, microwave, microwave, like that. Yeah, so we also learn some other we also learn some traveling wave, we can represent it in a sinusoidal wave, because those traveling waves can they move in simple harmonic motion. So we can also use simple harmonic motion form to represent the traveling wave. Yeah, so for the in the chapter 15, we mainly focus on the general idea, general things about the traveling waves. And in chapter 16, and we just focus on mostly focus on a stream wave and the sound wave. Yeah, we learn many things about the stream wave and the sound wave, how to calculate the velocity, the frequency, and the wavelengths for the stream wave and the sound wave. And if those wave they spread out in some specific situation, for example, in if the sound wave spread out in a tub, how to represent this wave and how to calculate this wave. Yeah, we learn about this. And in chapter 15, we focus on the stream wave and the like the sound wave. And today we will talk about the wave optics. Yeah, like we mainly focus on the light wave. Yeah, in this chapter. Yeah. So let's begin today's class. And let me share my screen. Okay. Yeah. Yeah, like you can see today we will like mainly focus on wave optics. And let's talk about, sorry. Let's talk about uh like a this chapter's goal. Yeah, for this chapter, we mainly focus on understanding and applying the wave model of light. Yeah, like I said, sorry. Yeah, like I said, in this chapter, we focus on the wave model of light. Yeah, and try to understand it and apply it. Yeah, this is this chapter's goal. And before we start this chapter, let's preview, like looking ahead, what we will learn in this chapter. Yeah, and you can see, firstly, we will learn the wave model of light. Wave model of light. You can see the varying colors reflected from this DVD can be understood using the wave model of light, which is the focuses of this chapter. You will learn how the wave model explains the interaction of light with small-scale structures. Yeah, you can see the light has they have some specific wave model, and these wave models can explain many uh, phenomenal in the real world, such as this DVD, like they can reflect some colorful some colors, and some also, for example, like the beetle, you can see the beetle, you also can see some colors from this bug, and also some other phenomenal, for example, the light, that the rainbow, yeah, the rainbow, yeah, similar things like that, many things similar like that. And after we learn the wave model of light, we can explain that. Okay, and yeah, then we will talk about the interference. Yeah, this the interference. I think you are now you are familiar with this one, because we have already talked about the interference for the sound wave. Yeah, and actually for the light wave, it also has the interference, like a phenomenon, and we will learn what is it and how it works. And you can see this bright colors no peacock feathers result from the interference of light reflecting from multiple layers in the feathers. You can, if you observe the peacocks, you will know, it's very colorful, it's very bright. Yeah, actually this kind of black colors of peacock, the result from the interference of light reflecting. Yeah, we will talk about this. And also you will learn how multiple light waves can interfere constructively or destructively. Actually, you can see after we talk about after we learn the chapter 16, like chapter 17 is now difficult for us, because we have learned many terms and many ideas based on the sound wave. Yeah, the sound wave also have the interference, also have some wave model. So it's a similar thing, just maybe a little change. Yeah. So yeah, this the chapter after learns chapter 16, and it will help us to easy learn chapter 17. Yeah, let's continue. Okay, we also will talk about diffraction. Yeah, like the light waves passing this swing needle are slightly bent or diffracted, causing the bends seen in the fridge. You can see here. If the light, sorry, if the light through this swim needle, actually the light will bend, or we call it diffracted. And yeah, we will talk about more about this situation and how to like explain this. And you will learn how diffraction occurs for light passing through a narrow slit or a small circular painter. Yeah. So we will talk about more about this later. And yeah, this is the chapter 70 we will focus on. And then before we talk about chapter 17, let's look back these things, the interference of two sound waves. Yeah, we have already talked about this in like chapter 16. And in section like 16.6, you study the interference of sound wave. There are two different loudspeaker. We will use these same ideas when study the interference of light waves in this chapter. Actually, it's a similar thing. Yeah, but just like we have already talked about the sound wave. Here in this chapter, we just mainly focus on the light wave. Yeah, you learn that waves interfere constructively at a point if their path length difference is an integer number of wavelengths. Am I right? Do you remember that? And how about the constructive situation? Do you remember? It will be the integer number of wavelengths plus half wavelengths. Do you remember that? Yeah, actually, in this chapter, we will also use these ideas to analyze the interference of two or multiple light waves. Okay, and before we talk dive into like chapter 70, and let's try to stop to think this question. Sound waves spread out from two speakers. The circles represent question of the spreading waves. The interference is like which options is right. Like here, there are two different sound source, and this is one and this is two. Let's see those 2 points. For the point one, and it is in the like point one is in the source one's crest, also in the source two's crest, which means for this point should be constructive. Am I right? Because it's all it is here. It is two like crest. It will plus together. It will like constructive. And for the point two, it is in the for the is in source one's crest, and but it is in the for source two's zone. That makes sense to you because it's now in this circle, in this circle, am I right? So it should be like this one, it should be destructive. Does it make sense to you? Yeah, so constructive at one, and destructive at two. Does it make sense to you? So the right answer should be C. Okay. Yeah, like I think this one is easy for you after we learn the chapter 16. Am I right? So let's talk about today's goal. And firstly, let's try to understand what light is. Actually, I think the light is very common thing in our real world. Every day you can see the light, you can feel the light. Yeah, but what is light? Yeah. So let's try to dive into these questions and talk about what is light. And then we learn about light interference. You can see sometimes that different labs, if they meet with each other and they will have some like interference situation. Let's talk about this one. And finally, we will explore diffraction gratings. Actually, this is a very common phenomenon for like light wave. And we will talk about like why it happens and like how to define it and how to calculate the like the wavelengths and the velocity things like that. Okay, let's continue. Yeah, and firstly, let's talk about what is light. Yeah, actually, for the light, I think you can like when you think about light, many things will pop up in your mind. Like under some circumstances, light acts like a particles traveling in straight lines. You can see sometimes when you walk in a forest, and that light like through the leaves, and it's just sometimes you can see a straight lines. Does make sense to you? It's like the particles traveling in a straight lines. If you like work in a forest, sometimes you can see this situation. And in other circumstances, light showing the same kind of wave like behavior as sound wave or water waves. Sometimes when you yeah, this one is very difficult to describe, to see it sometimes. Yeah, but like the light, yeah, sometimes it just act like a wave. We call it light wave. Yeah, and change the circumstances yet again, and light exhibits behavior that is neither wave-like nor particle-like, but has characteristics of both. Yeah, why it is sometimes light light acts like a straight line, like a particle traveling string. Sometimes it just acts like a wave. Yeah, because you can see like the lab like has both characters of like a wave and a particle. Yeah, we call it has both both wave-like and particle-like for the light. Yeah, then here we develop three models of light. Each model successfully explains the behavior of light within a certain range of physical situations. Yeah, let's talk about those three models for now. And the first one is wave model. Yeah, under many conditions, light behaves like sound or water waves. Phenomena such as the bright colors of a human bird or the blue sky are best explained using the wave model of light. Yeah, sometimes like the human bird and some bright colors, some beetles and some DVD. Yeah, this light is kind of like if you explain it using the light wave model, and yeah, you can explain it very well. We introduce some aspects of this model in chapter 15 and 16. Actually, we have already talked about the wave model, but not too much light. Just like the stream model or like a stream wave or like the water wave. But actually, since like the light, sometimes it behaves like a wave. So it has the same characters with water wave or sound wave. We have already talked about some aspects in chapter 15 and 16. Yeah, in this chapter, we focus on wave optics, and wave the study of light's wave behavior. So we have already talked about some characters in chapter 15 and 16 for the sound wave or water wave. Sometimes we talk some I think we have already talked about some in for the light wave, for example the interference thing a little bit. But in this chapter we mainly focus on wave optics. Yeah, and the lights wave behavior, and this is the wave model. And the ring model, you can see the behavior of prisms, mirrors, lenses, and optical instruments like telescopes and microscopes is best understood using the ring model of light. You can see sometimes the light is just like a straight line, like the light particle just traveling in a straight line. So we can try to explain something using for example the mirror, lenses, prism, like some optical instruments in using ring model. Yeah, and which treats light as traveling in straight line paths called rings. This model known as ring optics. Yeah, we will focus on ring optics in the next chapter. Yeah, this chapter we just learn the wave model for line, and this next chapter we will focus on ring model for light. Yeah, don't worry about you are confused about this part. Yeah, we will learn that. Okay, and also we will for the light it has the other like a model can describe it or explain it. Yeah, we call it fountain photon model. Yeah, modern technology increasingly depends on quantum quantum like physics. In this realm, light is made up of photons, particles that exhibit both wave-like, yeah, both wave-like and particle-like behavior. Photons are the fundamental unit quantum of light. Well, much of quantum theory is beyond this scope, the scope of this course. We will explore its key ideas in chapter 25. Yeah, like actually the fountain model, like sometimes like in some situation, in some like phenomenal, like the light acts like wave and light at the same time. So we call this photon model. Yeah, we will like talk about some details in chapter 25. Yeah. Okay, this is the three model for light. Yeah, you can see the light is a special thing. Yeah, it has it sometimes it acts like a straight line, like we can explain it in a rain model, and sometimes it likes a wave, so we can explain it in wave model, and sometimes it like express like two different like characters, like the wave-like and the particle-like behavior. So we can like explain some situation using both like a model, like we call it photon model. Yeah, we will talk about more. Yeah, in chapter 25. Okay, today let's try to like talk about first let's try to talk about the propagation of light waves. Yeah, you can see a water wave passes through a window-like opening in a barrel. Here there is a sorry. Yeah, there is a opening. It's just like a window, and the wave spread out to fill the space behind the opening. You can see this is a wave, the water wave. Yeah, like it goes through this window, and you can see this wave spread out to fill the space behind the opening. Now, this phenomenon is called diffraction. Yeah, actually, you can see this like a phenomenon called diffraction. I think you guys know this situation, am I right? So diffraction is a clear sign that whatever is passing through the opening is a wave. Yeah, like a diffraction is a clear sign that like whatever is passing through the opening is a wave. Yeah, does it make sense to you? Yeah, like if a wave passes through a window and it will have this situation, a phenomenon. We call this diffraction. Okay, let's continue to talk about the propagation of light waves. And when the opening is many times larger than the wavelength of the wave, you can see here in this situation, this is the wavelength, am I right? This is the wavelength from here to here. This is the wavelength, and you can see the opening seems like a close or smaller than it, and there will be the diffraction phenomenon. And sometimes when the opening is many times larger, yeah, you can see this opening. Yeah, this opening is very large, and it's larger than the wavelength. You can see here is the wavelength of the wave. The wave continues to move straight forward. You can see this is the original wave, and then through this like a window opening, and it is just keep the same thing. Am I right? There will not be a diffraction phenomenon. So yeah, that makes sense. Yeah, there is a defined region, the shadow, where there is no wave. Yeah, actually here, there is a defined region, like we call it the shadow, where there is no wave. Yeah. This is similar to the straight line. appearance of light with sharp shadows as light passing through the large windows. You can see through these large windows, there is no like some wave. It's just like the light just go through this window. Yeah, and if there is it is a block, there is no light. Does it make sense to you? Yeah, and whether a wave spreads out, like or travels straight ahead with sharp shadows on either side depends on the size of the objects with which the wave interacts. You can see here, the like uh, if a distraction situation happens, which depends on the size of these objects with which the wave interacts. Yeah, and the diffraction becomes noticeable when the opening is comparable in size to the wavelength of the wave. Yeah, like diffraction becomes noticeable when the opening, this opening is comparable in size to the wavelength of the wave. Like if it is close to the wavelength of the wave, or smaller than a little small, or like similar, a little bigger, yeah, that's fine. Yeah, but if it is too large, there will be no like a distraction phenomenon. Does it make sense to you? It's just like go through the what like the wave just move straightforward. Yeah, this is like the water wave, like acts like that, and the light wave also acts like this. Yeah, and like light, actually light is an electromagnetic wave. We have already talked about this like before, because light can be spread. Why it is electromagnetic wave? Do you know that? Actually, I talked about this before, because you can see light can be spread out, not based on the medium, like they don't need the medium to spread out. Does it make sense to you? Light can be spread out in a vacuum environment. Does it make sense to you? Yeah. So like light consists of very rapidly oscillating electric and magnetic fields. Yeah, because it consists like oscillating electric and magnetic fields. Yeah, it is an electromagnetic wave. Yeah, sorry, all electromagnetic waves travel in vacuum at a speed of light. This one, sorry, I think I just should put it here. Visible light wavelengths lenses range from 400 nanometer to 700 nanometer. This is a visible spectrum. Actually, I think I have already like show this to you, like in the like light spectrum, and from 700 nanometer to the from 407 nanometer to 700 nanometer, from red to the like purple. Do you remember that? Yeah, this is a visible spectrum. Our eyes can see the light if the wavelength between in this range. Because the wavelengths lenses are very short, the frequencies of visible light are very high. Yeah, because you can see. Okay, why it is just like that? Because V equal what? Lambda multiple F. Am I right? And V is the same thing, like it's just this one, like a vacuum at the speed, like it's just like even in air, it's a similar value, and V is a fixed thing. And you can see if the frequency for now the wavelength is very small. Am I right? If you F equal V divided lambda, am I right? Like which means if this one is a fixed thing and this one is very small, which means the frequency is very high. Yeah, there is an example for 600 nanometer. The wavelength is just like this. Yeah, just try to remember this equation. It's very important. Yeah, you will use it very often. Okay, let's continue to talk about. Let's talk about the other term, like the index of refraction. What is index of fraction? Actually, the light waves, like slow down as they pass through transparent materials such as water, glass, or air. Yeah, this is due to the interactions between the electromagnetic field of the wave and the electrons in the material. Yeah, actually, this is just like give us like the light waves slow down. Yeah, in the vacuum, this is the speed. Yeah, in the vacuum, the speed is v vacuum equal c equal 3. Uh, yeah, and the light waves slow down when they pass through transparent materials such as water when it like spread like a pass through from the vacuum to air or to water or to glass. Yeah, like the speed will goes down. Yeah, this is due to the interaction between the electromagnetic field and wave and the electrons in the material. All the speed of light in a material is characterized by the material's index of refraction n. Yeah, we define this n equal this one. Like the speed of light in a vacuum divide the speed light in the material. C divided V, we got it n. N is always greater than 1 because V is always less than C. Yeah, because you can see like the light in the vacuum is uh, is is a fastest speed. If because if the light pass through other material, transparent material, it always smaller than C. Yeah, so which means a vacuum has n equal 1 exactly, because if you can see, if I just put here spin of light in vacuum, this one is C, is 1, am I right? And and let's see some like a common typical indices of refraction. You can see for the vacuum it is 1. Yeah, like n equal C divide C. For the air, which means from the vacuum to the air, it is 1.0003. Yeah, which means what? Which means the like the V in the air is very, very similar in the vacuum. Am I right? So that's the reason why when we calculate when we try to resolve some problem, even it is in the air, like we just use like a 3 multiple 10 power 8 per second. So we use this value because you can see this one and this one is very close. Am I right? And in the water, the index of refraction is 1.33, and in the glass, it is 1.5, and in diamond, it is 2.42, which means that the speed will like goes down and slower. Yeah, does it make sense to you? Okay. This is just like by the measurement. After measurement, we just get these typical indices of refraction. Okay, and yeah, the frequency of a wave does not change as the wave moves from one medium to another. Actually, you can see the velocity change after when the light waves pass through from one material to the other, but the frequency of wave does not change as the wave moves from one medium to the other. Yeah, which means what? Which means if we know the velocity equal what? Lambda f, which means f will always keep the same, which means if the velocity goes down, the wavelength goes down, the velocity goes up, the lambda wavelength goes up. Yeah, because the velocity, the frequency does not change as the wave moves from one medium to the other. You can see. Therefore, the wavelength must change. Doesn't make sense to you. The wavelength of light in a material is this is the wavelength. If it is like a velocity here, and it is V divide F material, and you can see like uh, we know like the n equal what? N equal V like C divide V, am I right? So which means V equals C divide N, am I right? So that's the reason why I just replace V with C divide N here. Am I right? So this we can get this equation, and also like a C divided F. What is it? It is a lambda, like a vacuum. Am I right? Like a C equal what? C is just the velocity in vacuum. Lambda F, like a vacuum. Am I right? So which means the wavelength in the material equal like the wavelength in vacuum divide n. Does it make sense for you? Which means the wavelength, because the n always greater than 1, the wavelength in material will always smaller than the wavelength in vacuum. Does it make sense to you? Yeah. So yeah, the wavelength in transparent material is shorter than the wavelength in vacuum. Yeah, we have talked about this. Okay, let's continue. Okay, let's review some quick check questions. Yeah, the first one is like a light wave travels as a plane wave from air. Yeah, and this is just approximately value because it is equal 1,0,0,0,3 and is around 1. Am I right? Into glass, it is n equal 1.5. Which diagram shows the correct wave fronts? We have already talked about that. When the light wave travels from air to the glass, which means the wavelength should be shorter. Am I right? Should be shorter like a uh than before. So yeah, this one is just the larger. This one is the same thing, same thing. This is shorter. So what should we choose? This one, am I right? C. Okay, yeah. Let's talk about one example. Yeah, let's try to analyzing light traveling through glass. Yeah, orange light. Here there is a specific light, orange light with a wavelength of 600 nanometer is incident on a 1 millimeter thick glass microscope slide. What is light speed in the glass? How many wavelengths of light are inside the slide? When the light enters the glass, its speed decreases. Am I right? Yeah. So we have already talked about that. The wave in the vacuum is is always the biggest value, and in other material the speed always decreases. So that also for its wavelength we have already talked about you for this using these equations, and the wavelength in materials always smaller than in the vacuum. So we'll compute both of these changes using the index of refraction of glass. Once we know the wavelengths, we will determine how many wavelengths fit inside the thickness of the slide. Yeah, like table 70.1 gives the index of refraction of glass is 1.5. Yeah, this table. Yeah, here glass 1.5. So then we can calculate the velocity in glass, the light velocity in glass using the equation, this one. This is the yeah. Yeah, this is the 71. Am I right? We can using this equation to calculate the velocity in glass. Okay. Yeah, like a V glass equal C divided N glass. Yeah, I think then you can easily to get the velocity, the light velocity in glass equal this one. Am I right from this equation? Like because in air equal 1.003, the wavelength of length is very close in air and vacuum. So we can consider that same. Yeah, we have already talked about. So the wavelength in the air, we consider it is 600 nanometer. Thus, the wavelength inside the glass is yeah. We can use this equation: lambda glass equal lambda vacuum divide n glass. We use this equation, and then we can got 400 nanometer. Yeah, and you can see, for now the glass the glass thick is 1 millimeter. So which means we need to know how many wavelengths in this glass. Which means we just use like the this is the like this is like a glass stick, yeah, and then it can contain how many, and this is one wavelength. So this is how many wavelengths this like a glass can contain and can include. Does this make sense to you? Because one wavelength is just for this one, and this is the total length, and this is how many wavelengths it can include. Does it make sense to you? Yeah, because n wavelengths span a distance d equal like n lambda. So the number of wavelengths in d equal 1 millimeter is this one. Yeah, you can see the wavelength of light is quite small. So we expect a large number of wavelengths to fit inside the slide. Yeah, does this make sense to you? This is 250, like 100. Okay, yeah. Okay, let's continue to talk about, yeah. Then let's talk about the section 70.2, the interference of light. Yeah, in section 16.6, you learned that the waves of equal wavelengths from two sources can overlap and interference. Yeah, we have already talked about this in chapter 16.6, like for the wavelengths and for the sound, for the like sound wave and for the water wave, they will overlap and interfering. And interference is inherently a wave phenomenon. So if light acts like a wave, we should be able to observe the interference of light waves. Yeah, the truth is, yeah, we can. Yeah, the laser light through a narrow, there is a laser light, yeah, through a narrow opening, we call it a slit, should spread out. Yeah, this is the we have already talked about the this phenomenon. Sorry. Yeah, propagation. If the opening is small and there will be a diffraction. Yeah, this is a diffraction situation. So for this, yeah, if there is a laser light through a narrow opening, we call it a slit, and then it will have a diffraction situation. Yeah, this is what we have already learned about this, and you can see there is a very famous experiment, Young's double slit experiment. Yeah, let's talk about this experiment and to see what we can learn from this experiment. Yeah, in order to observe interference, we need two light sources whose waves can overlap and interfering. Yes, it makes sense. I'm right. If we want to learn the interference, we need two light sources. Like in an experiment first performed by Thomas Young in 1801, light, in our case a laser, is showing through a pair of slits. Like here, a pair of slits means there are two slits. It is a double. You can see 1, 2. Yeah, light passing through the slit strikes a waving screen. There is a waving screen, and this light passing through those two slits. And you can see because the slits are very narrow, the light spread out behind each slit. And those two, here is one, here is two. Those two spread waves overlap in the region between the slits and the screen. And then it will, yeah, you can see it will overlap and interfere. And you can see the constructive interference occurs when the distance here, if for example, here is R1, R2, when the distance R1 and R2 from two slits differ by a whole number of wavelengths. At this point, the screen, you can see here, here, the screen will be bright. This is a constructive interference. And if the distance R1 and R2, it is like a whole number of wavelengths plus half of wavelength, there will be like a destructive interference. At this point, the screen will be dark. You can see. Let's change another. Yeah, here, here, here. Yeah. Do you feel the familiar? Do you feel familiar? Yeah, it is similar like a water wave, like the sound wave. We have talked about that before. Yeah, there are two different waves like a source. Sorry. There are two different sources, and if this like if this for this point, if the difference is like just the whole number of wavelengths, and it will have the constructive interference. If it is the difference like the path length difference, it is like the whole number of wavelengths plus half of wavelengths. Like here is whole number of wavelengths. Here is a whole number of wavelengths plus. Yeah, it will have the destructive interference. Yeah, similar thing. I'm right. So, like along the screen, you can see along this screen. This is like a view of screen. The difference, like a delta R, alternates between being a whole number of wavelengths and a whole number of wavelengths plus half a wavelength, which means like here it is half wavelengths. The difference is half half like not half. It is like a whole number of wavelengths. Here is half whole plus half. Here is whole number plus half. Yeah, you can see. Uh, and then here and here. Yeah, yeah. These ideas to a series of alternating bright and dark bands of light called interference fringes. Yeah, those kind of situation. And yeah, those kind of situation like one like the constructive interference, this constructive interference, constructive interference, like a bright dark, bright dark. This bright dark bands of light, we call it interference fringes. The center maximum, the central maximum, here is the central maximum, is the brightest fringe at the middle point of the screen. Yeah, here is the brightest fringe at the midpoint of screen. Does that make sense to you? Let's continue. Like so let's analyze like those this double slit interference. Like the double slit slit experiment consists of a double slit spaced d apart, which means here this one. So those two slit it is d, and a distant L is this like a berry to the view screen. This is L, and we assume L is very much larger than D because we talk about that if the D if here if the like those D is very big, and it will like it will not have the diffraction situation. I'm right. So we suppose this D is very small and L is very much like larger than D. And the constructive interference occurs when the difference is like the integer number, the whole number, like wavelengths. Yeah, we have already talked about this one. And it produces a bright fringe at that point. And we must find the position on the screen where the difference, this difference, like the different path length difference is a whole number, like a wavelength. At that point, it will be a bright fringe. Does it make sense to you? We have already talked about like for the experiment, and a point P here. For example, here is the point P on the screen is a distance y. here y. Here is y. Y from the center of the view. Here is the center view of center of the view screen. Oh, it is like a angle theta. Here is theta. From the line like connecting the center of the to the center of the screen. Yeah, here from here, this is the theta. So the y equal what? Y equal L because this is L, this is y. So y equal L tangent theta. Yeah, from this from this triangle. Does it make sense to you? Because point P is very far compared to the spacing between cells. Yeah, here is. So the two passes to point P are virtually parallel. You can see here, I think it's not very easy to understand. Yeah, we know, we have already know how this equation get, am I right? Because yeah, you define this is theta, and this is L, and this is Y, and then it is obvious Y equal L tangent to theta, am I right? And because point P is very far, compared to the spacing between cells, like this one, this D, this like a P, it is like the distance, the point is very far compared to this D. The two passes to the point P are virtually parallel. Yeah, like if you because it is very close, so you just zoom in it. Those two like seems parallel. Yeah, does it make sense to you? Okay, then therefore the path length difference is the short side of the triangle. Yeah, let's talk about why it is just like that. You can see here, actually, if you, here is just like the theta, and those two is just a parallel, and this is D. And you can see if you, here is a 90 degree, and you will see here, which means if it is parallel, this seems like a 90 degree, this is 90 degree, this like a, because this is parallel, so this is parallel, so this angle equal this one. And then here is D, here is delta R, like the difference between two paths, which means delta R equal what? D sin theta. Does that make sense to you? Yeah, because here we just like consider this is theta, and this is a 90 degree, and this is like that degree, which means here is 90 degree, here is the similar, this theta, this angle equal this one theta. Am I right? Does it make sense to you? Yeah. So which means so we can get this equation, like the difference the path length difference is this short length of triangle, this one, and it equal D theta sin theta. Yeah, we can get from this analyze. And then so the bright fringes occur like because we know like this is a path length difference. So if this path length difference equal whole number wavelengths, and then it will have the bright fringes. Does it make sense to you? Yeah, the center of the view screen at 0, y equal 0, is equally distant from both slits. So here the if it in this situation, yeah, the like path length difference is equal 0 with m equal 0, which is where the brightest fringe occurs, because like two same waves, they just plus together. So it is the brightest fridge. Does it make sense to you? Okay. In general, the amps bright fridge occurs when one wave has traveled m wavelengths farther than the other, and thus, like a difference is m lambda. Yeah, the m's brightest occurs like when one wave has traveled m wavelengths farther than the other, and yeah, does it make sense to you? Okay. And then the condition for the angles at which bright fringes are observed as, yeah, because we know like the d sin theta equal what, m lambda, am right? So sin theta equal m lambda divide d. Yeah, so we can like represent sin theta using the m lambda and d. M, which means like the like which one, like which bright fridge, like here is 0. If here is 0, for example, if here is 0 and here is 1, here is 2, here is 0, here is 1 2 3 4, 1 2 3 4. Yeah, it is like a as the same thing in different direction. Yeah. Okay, let's continue. Using the small angle approximation. Yeah, we used this before, like in chapter chapter 14. And if the theta, this angle is very small, we can use the small angle approximation, like sin theta equals theta. We can see that the theta m equal m multiple lambda divided d. So because here equal theta m, and we got this equation. Using this angle, we find the m spread fridge occurs at this one. Why? Yeah, because we have this thing. Am I right? So, which means y equal L tangent theta. Am I right? And the tangent theta, if in a small angle approximation, it also equal L theta, which means it equal L m lambda, which equal m lambda L. Does it make sense to you? Yeah, we just use the small angle approximation. Okay, let's continue. Yeah, the equation. So this equation, yeah, this equation show that the interference pattern is a series of equally spaced bright lines on the screen. The fridge spacing between fridge M and fridge M plus 1 is, yeah, you can see we can let the difference fridge like a distance ym plus 1 minus 1m, and this is ym plus 1, and this is ym. It's just equal what? Lambda L divided D, am I right? It is just you can see the wavelength is fixed for a specific wave, and this is L. It is from the it is from here to here. It is also the fixed thing, am I right? So and D and it also is fixed thing. So like the interference pattern is a series equally spaced bright lines on the screen. Yeah, does that make sense to you? Okay. So let's check about the dark fridge. The dark fridge, which means destructive interference, are bands of destructive interference where the path length difference of the wavelengths is a whole number of wavelengths plus half of a wavelength. Actually, this situation is similar with constructive interference. Only like you use for the constructive interference, the delta R equal m lambda, but here the delta R equal m plus half lambda. So we use the relationship of the path length difference with the angular separation of the fridge found earlier. we have this one. So here, this is for like a constructive. This is for constructive like a interference. So for this constructive, we have So here is for the constructive. For the inconstructive, it should be it it should equal m plus lambda. M equal what? D sin theta, which means sin theta equal divided D. And then use the same process, we can get, combine the previous equations. We found that the dark fringe are located at the position, this one here, m plus 1 divided 2 lambda L, multiple L divided D. Yeah, this is for the dark fringe. And for the like a bright fringe, it is just m. Here, we just replace this one with m. Does it make sense to you? The dark fringes are located exactly halfway between the bright fringes, because you can see the bright fringe is lambda L D and 2 lambda L D. But here is just like a half, like a like a 0 half, like a lambda LD, the 3 lambda LD. Yeah, it's just a half. Yeah, here is the bright one, the dark one, bright one, dark one. Does it make sense to you? Okay, let's continue. And the intensity of light oscillates between dark fringe, where the intensity is 0 and the bright fringe are of maximum intensity. Yeah, for the light intensity, because here it is here is a dark fringe, so the intensity will be 0. So it is totally like you cannot see anything. But here the bright fringe, it is the maximum intensity, so you can see the like all the light here. Does it make sense to you? Yeah. Yeah. Why this situation happen? Because why this situation? Because the fringe intensity decrease, because the light intensity from each slit by itself is not uniform. Yeah. If you do this lab, and you will find it will like if the wave is just like that, and this wave just like that, and you can see like and the edge here, it will be the intensity is not that strong, but here the intensity is the most strong. Yeah, does it make sense to you? Okay, let's continue. Let's view some quick check questions. And laboratory experiment produces a double slit interference pattern on the screen. The point on the screen marked with a dot is how much farther from the left slit than from the right slit. Yeah, so you can see like marked is how much further from the left slit than from the right slit. It just asks us like how far, how much further from the left sheet than from the right slit, which means we need to calculate delta lambda, delta 2 divided delta 1 equal m lambda, am I right? So which means here is 0, am I right? Because this is central maximum. So which means this is 1, this is 2, and let me change it another 0, 1, 2, which means here is the difference should be 2 lambda, am I right? So which means the answer should be C. Does it make sense to you? Okay. Yeah, 2 lambda. Okay, let's quick check this question. A laboratory experiment produces a double slit interference pattern on a screen. If the screen is moved farther away from the slits, the fringes will be like this fringes, like this like a question just let us to try to decide the delta L, like how this fridge like change. So this is the difference, like the difference between two bright fridge is equal what? Lambda L b divided D. Lambda is the same thing, am I right? But the screen is moving further away from, which means the L become bigger, am I right? So which means this delta Y should increase, am I right? So which means it will be further, not closer. This Y will become bigger. Yeah, so which means this one. Does it make sense to you? Yeah, it's with further apart. Okay, let's talk about this question. A laboratory experiment produces a double slit interference pattern on a screen. If green light is used with everything else the same, the bright fridges will be. Yeah, actually, this one is very similar with the last one. Yeah, it just let us to tell what's the difference, like the delta Y compare with the original one. Like if which one is equal what is equal. We have already talked about it. It is equal lambda L divided D, am I right? So, and other things are the same, but it changed the green light. Green light, yeah, we have already talked about it in like lecture 5. Yeah, here you can see the green light has a smaller wavelength. Yeah, for the wavelength, it has a smaller wavelength, which means this one decrease, which means this one decrease, which means here to here like a smaller, which means it is closer together. Does it make sense to you? So this should be A, closer together. Yeah, we should use this equation and found the green light has a shorter wavelength. Okay, let's continue to talk about the other one. A laboratory experiment produces a double slit interference pattern on screen. If the slits are moved closer together, the brighter fringes will be. Yeah, it's a similar thing. We just write the equation, lambda, like a lambda y equal like a delta y equal lambda L divided D. For now, and the D, you can see the slits are moved closer. Yeah, which means the D is is decrease. Am I right? So which means this one increase. So which means it is further apart. Does that make sense to you? Yeah. So it should be C. Okay, let's continue to talk about one example. Measuring the wavelength of light. Yeah, a double slit interference pattern is observed on a screen 1.0 meter behind the two slits spaced 0.3 millimeter apart. From the center of one particular fridge to the center of the length bright fridge from this one is 1.6 centimeter. What is the wavelength of the light? Actually, yeah, you can see we just need to get all the information and use the equation we have already know, like this equation. 17, like if it is not always obvious which fridge is a central maximum, slight imperfection in the slits can make the interference fridge pattern less than ideal. However, we don't need to define the m equals 0 fridge because we can make use of the fact, like express in equation this one. Like, what is this one? It just lambda L divided D. So that is the fridge spacing lambda Y is uniform, which means it is just like the same thing. It's uniform. Yeah. So the interference pattern looks like the photograph, figure 17.6b. Yeah, it's just like this image. Yeah, if there is a double slits, and then for the either viewing of screen, and you will see like this one is bright, this is a dark, bright, 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 bright. It's a uniform like a uniform situation, which means the distance is the same thing, because delta y equal what? Delta y equal lambda L D. Yeah, lambda usually for a specific one it is fixed. L, yeah, it is fixed. D is fixed. So this one is fixed. So the distance is the same thing. Does it make sense to you? So let's continue. So like the fridge spacing is yeah, lambda y equal what? Lambda y equal delta L D. And here D is what? Here the D is 0.3 millimeter. Am I right? And screen is 100. This is L. So yeah, let's talk about it. And this is one. Yeah, because it is just like the uniform, like so the distance should be the same thing. The distance should be the same thing. So from 0 to 9, here is this. We know like from the center of one particular fridge to the center of the non-spread fridge, from this one is 1.6, which means from from 0 to 9, and the distance should be equal 1.6, which means one for one is just 1.6 divided 9. Does it make sense to you? Okay, sorry. Divide 9. This is the delta y. And then we use this equation. We know this one, and we know this one, and we know this one. And lambda equal what? Lambda, lambda equal delta y multiple d divide L. Am I right? So this is just the delta y multiple d, and this is the L. This is the this is a D, and this is a L, and this is the delta Y here. And we just got the wavelength 530 nanometer. It is customary to express the wavelength of visible light in nanometers. Be sure to do this as you solve problems. Yeah, we've noted that the visible light spans the wavelength range here. Here from like 400 nanometer to 700 nanometer. So finding a wavelength in this range is reasonable, am I right? So if it is out of this range, you should like know maybe there are something wrong. So yeah, like for these questions, yeah, firstly you use like those different space is the same thing. So this space is the same thing. And from 0 to 9, it is 1.6. So for 1, it's just a 1.6 divided 9. And then you just get the delta y. And from this equation, you can get the lambda. Yeah, does it make sense to you? Okay. Let's continue to check about the other examples. And two narrow slits 0.04 millimeter apart are illuminated by light from a Harnell laser. The lambda equal what? This one. What is the angle of the first bright fringe, and what is the angle of 70th like a bright fringe? Yeah, since like we know like from this equation we need to know the m here, we know that, and lambda, and here we know that. Am I right? And d we know that. So for the first one, it's just a sin theta 1 equal what? Lambda d. And am I right? Equal what? Equal 6 nanometer divide millimeter. Yeah. Notice the unit, and it around like let me try to calculate it. Around like it is around 0.91 degree. It's very small. And for the 30s, yeah, it's the same thing. Yes, same 30 equal what? 30 uh, yeah, it's just a 30 multiple point degree. It's around like 27 degree. Yeah, that makes sense to you. Yeah, even at this relative large angle, this equation also work. Okay, let's continue to talk about the other one, the other thing, the section 17.3, the diffraction grating. Yeah, what is diffraction grating? A diffraction grating is a multi-slit device. Actually, you can see just now we talk about only like a two slits. Here, two slits. Here is just a two, one, two. But if there are like multiple slits, yeah, there is like a device. We call it a diffraction grating. It is a multi slit device. The Krasnov plan wave arrives simultaneously at each silt to be in phase with a wave emerging from every other slit. Each wave will spread out and interfere with each other wave and interfere. Yeah, that makes sense to you. Yeah, like when the light goes through this like slits, and it will like each wave will spread out like such as that, and those like wave will have the will interfere with each other. Does it make sense to you? It makes sense, am I right? So let's talk about how the interference. Okay, the distance L to the screen. For example, here, I think I just should put this okay. Let's talk about yeah, I just need to put this image to this slides. I will change it later. Yeah, the distance L to the screen is very large in comparison with the slit spacing D. Yeah, here this is the spacing D. Yeah, here is D. And hence the path followed by light from one slit is very nearly parallel. Yeah, so it is parallel to the path from the neighboring slits. Yeah, we have already talked about it. It's similar with the two double like slit. Yeah, and the wave from one slit travels distance delta r to equal d sin theta less than the wave below it. Actually, we have already analyzed this just now, like here. For example, these two, and we just here we connect these two, and this one is theta. So this distance is delta r equal d sin theta, which means this one is less than this one with this distance. Does it make sense to you? So this one is shorter than this one is shorter than this one, and this is the value. Does it make sense to you? Yeah, here. Yeah. Okay, let's continue. Like if the angle is such that the delta r equal if this equation like works, then the light wave arrives at a screen from one slit will travel exactly m wavelengths more or less than light from the two slits next to it. So the waves are exactly in phase. Does it make sense to you? Yeah, if the angle is such that, yeah, it's just like this equation works. Yeah, we talk about that. Then the light wave arriving at the screen from one slit, will travel exactly wavelengths more or less than light from the two slits next to it. Yeah. Here, for example, here is lambda. Yeah, here is 2 lambda, here is lambda, here is 0, here is lambda, here is 2 lambda. Yeah, it's just like a more or less than the light from two slits next to it. Does it make sense to you? We have already talked about it. Yeah, actually, this is similar to the double slits, but yeah, the similar thing. Okay, let's continue talk about n light waves from n different slits with all being phased with each other when they arrive at a point on the screen at an angle theta, such that this one, yeah, if those n light waves from n different will be in phase with each other, arrive at a point. Yeah, this is a theta. And the position Ym of the m's maximum is this one. Yeah, the integer m is called the ordinal diffraction. Yeah, we can see here. Yeah, m is the order of the diffraction. But you can see like the difference between the double slit and the multi slits. You can see here, this one is not uniform. Yeah, that makes sense to you because you can see only when all the like light has uh the distance is m lambda, it has this bright like fringe. Otherwise, it will be dark. Am I right? So which means here is the brightest, yeah, from the middle, but the edge and but some point, all of them will be cancelled. Yeah. So this is an important difference between the intensity pattern of double slit interference and the intensity pattern of multi-slit diffraction grating. You can see here, this is double slits, this is 10 slits, this is 15 slits. The bright fringes of diffraction grating are much narrower. As the number of slits increases, the bright fringes get narrower and brighter. Yeah, you can see this one get narrower, narrower and narrower, and but brighter and brighter. Yeah, do you know why? Of diffraction grating are much narrower. As the number of slits increases, the bright fringes get narrower and brighter. Yeah, which yeah, you can see here. If there are only two like slits, and there are only two like light, they can be interfered with each other. And yeah, the intensity is just like the intensity is just a two get them together, plus together. Am I right? So it's not like that bright. It's bright. It's not that. But if there is 10, which means here it has 10 different like a source, different light wave plus them together. So which means it's brighter, the intensity is bigger. But you can see there are 10 waves. They will like cancel with each other. They just like plus at the specific like a wavelength is just like here, here, here. Other situation it will like cancelled with each other, reduce with each other. So which means for like it will like become like a narrower, but it's brighter. Does it make sense to you? Yeah. So this is for the diffraction grating. Actually, the equation for the diffraction grating is a similar thing with like a double slit grating, but the different thing is for the like a double slit. Yeah, you can see, it is like a it is uniform like a presentation, and also like the the bright fridge is wide, and but it's not that bright. But for the multi slits, and it is the bright fridge will be brighter, but it's narrow. Yeah, doesn't make sense to you. Okay, let's continue. Let's talk about one quick check question. In a laboratory experiment, a diffraction grating produces an interference pattern on a screen. If the number of slits in the grating is increased with everything the same, including the slit, then, okay, we have already talked about that. If the number of sitting ingredients increase, which means the bright it will brighter but narrow. Yeah, the fridge same no like same. Yeah, the fridge is stay in the same position but get brighter and narrow. So which means C is the right answer. Does it make sense to you? Yeah, it will in the same position but get brighter and narrow. Okay, yeah, the answer is C. Let's talk about one example. Let's talk exploring this diffraction from a feather. Like this is a biology problem. Yeah, if you gently spread the barbs on a feather and look through it at a light source, you will see a clear pattern of rainbows due to diffraction by the feather's bubbles, which are small, evenly spaced structures visible in the micrography below. You can see here is a micrography below. Like if the bubbles are spaced at 15 per millimeter, a typical value, what is the first order diffraction angle for blue light of 450 nanometer and red light of 650 nanometer? Okay, let's review this question. Yeah, the bubbles are evenly spaced. You can see from here. Yeah, you can see here. Yeah. The the bubbles are evenly spaced with open spaces between them. So the function as a diffraction grating, we will find the diffraction angles using equation like 11 equation 17.12. If you are familiar with if you are this one. This one is just the equation like 70.12. Yeah, we will use this equation. Let me write this one down here. Okay. Yeah. Sin theta m equal what? Equal m lambda d. Yeah, so we are told that there are 15 bubbles per millimeter. So which means in meters, the grating space is D. We can got it. This one divide 15 millimeter, like a point 0.020 millimeter, and then we change the unit to meter. Like this is the distance between the two bubbles. Yeah, and then like for two colors noted, the first order direction on angle is yeah here m equal 1, so we just move 1. Yeah, here is 1, and lambda, this is for the blue light, and divide d. This one is like a radiance angle, and this is for the red radiance angle, and transfer this angle to the degree angle. It is 1.3 angle, and this is 1.9 like degree. And in the photon of diffraction pattern from the further bubbles, the rainbow pattern has a small spread, so a small angle seems reasonable. So this small angle seems very reasonable. Does it make sense to you? So yeah, if you met this question, don't be afraid of that. Just use the equation we have already talked about. Actually, yeah, diffraction, like the multiple diffraction grating. It's a similar thing with double silts, and yeah, and you can see the equation. It's a similar thing. Yeah, if we went back to the double silt. Yeah, here. Yeah. Yeah, you can see it's the same thing. Yeah, the different thing is just like a it's just like a for the diffraction like gating. Yeah, and the like the bright for the bright fridge is the brightness and the like narrowness will be changed. Yeah, and by the like if you increase the like grating like the opening number. Does it make sense to you? Okay, let's talk about the spectroscopy. Spectroscopy. Actually, yeah, this is something you just know it. Like spectroscopy is the science of measuring the wavelengths of atomic and molecular emissions. Atomic elements in the periodic table emit light at a certain well-defined wavelength when excited by light, electricity, or collisions. Yeah, like we can use uh, the this like a light diffraction phenomenal diffraction equations to measure the wavelength of atomic and monocular emissions. So we can use this in spectroscopy. And by accurately measuring these wavelengths, we can deduce the various elements in a sample of unknown composition. Because their bright fringes are distinct, diffraction gratings are an ideal tool for spectroscopy. Yeah, actually, there are one example in textbook. You can review it. But this one is you just need to know like from based on the equation from like diffraction gratings, you can like measure the wavelength of atomic and molecular emissions like that. Yeah. Okay, let's talk about the other thing, reflection gratings. Yeah, it is more practical to make a reflection gratings like a mirror with hundreds of or thousands of narrow grooves cut into the surface. You can see here. There is a surface, but this surface is not like a smooth. Yeah, it's just like made by cutting parallel grooves in a mirror surface. The grooves divided the surface into many parallel reflection strips, which spread the wave. You can see here. If the incident light come here, come, and then this like grooves like a surface, like these grooves will like divide surface into many like parallel reflection strips, and which this strip will spread the wave. Yeah. Yeah, this we call the reflection gratings. The interference pattern is exactly the same as the pattern of light transmitted through n parallel slits. Actually, it's the same thing. When it will just yeah, just like here, 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 here. It's a similar thing, like just same as the pattern of light transmitted through n parallel slits. The calculations determined for the diffraction grating applies to reflection grating as well as to transmission grating. So you can also use the equation for the diffraction grating here, like to calculate the reflection grating. Yeah, the iron of holes on a DVD is used to transmit data, but optically they cause the rainbow colors observed. Yeah, yeah. This is why the DVD like surface is colorful because the reflection gratings. You can see if you observe this DVD in a microscope and you can see here are some like surface mirror surface. There are some like a groups. Yeah, does it make sense to you? Okay, let's talk about one example, like beetle colors. This is a biology example. Like you can see the hard outer coating of many beetles has microscopic structures that produce amazing colors. In some ground beetles, parallel ridges in the cortical function as a reflection grating. The source of the rainbow color in the reflection from the beetle in the photo. An analysis of the grating spacing can provide valuable taxonomic information. A researcher illuminated a specimen of a ground beetle with a beam of yellow light. Yeah, he just do an experiment and use a beam of yellow light with the intensity equal what? 500. I think this is lambda. This is wavelength 570 nanometer. The resulting diffraction produced a clear maxima at 30 degree and 25 degree. What is the spacing of the ridges that produces this diffraction effect? Yeah, let's talk about this example. Yeah, the strategy like the ridges are working as a reflection grating. Here are some like regions in the, yeah, sorry. Here are some like regions in the surface. These regions are working as a reflection grating. The spacing between the regions is a grating space. We can assume that the angle corresponds to the first two orders. So, like, yeah, here we know there are like two angle, yeah, like 30 degree and 25 degree, and so let's assume this is the first two order. So theta 1 equals 13 degree and theta 2 equals 25 degree. We can do a separate calculation of the grating space D for each of the angle. Yeah, so we can rearrange equation 17.12 to solve this questions. Yeah, you can see we can write the equation here. Sorry. Sin theta m equal what? Equal m lambda d. Am I right? So which means d equal what? D equal m lambda sin theta m. Yeah, for the situation one, the m equal 1, so d equal m just lambda divided sin theta 1. We know the lambda equal this one, and sin theta sin like 13 degree, and then we can calculate the distance is 2.5 mu m, am I right? And for the m equal 2, like we just here m, don't miss m is 2, and lambda is the same thing, and sin 25, and then we got 2.7 mu m, am I right? So yeah, we know like the two orders of diffraction are produced by the same grating, so they should give the same spacing. Am I right? You can see those spacing should same because we know the diffraction grating, the distance is should the same thing. So like they should give the details given in the problem are real numbers from a research paper. So the fact that the results do not agree exactly means that there was some uncertainty in the measurement. Our best estimate of the grating space is average of two results, 2.6 mu m. Am I right? But if you found that those two is totally different, or like have a bigger difference, there should be something wrong. But it's close. So we just like average them. Yeah. Yeah, the grating space is comparable to other gratings we have seen, and our two results are a reasonable match to each other, so we can have confidence in our result. If you calculate these two are totally different, you need to check what you have already done. That makes sense to you. Okay, this is yeah, this is what we talk about today. And let's summarize like this. And the in this class, we mainly talk about like the double silt in inference and diffraction gratings. Like the physical principles like underlying double slit interference and diffraction gratings are the same. Yeah, you can see those two actually it's the same thing is for the equation. Yeah, it is a similar thing. It's the same thing. A bright fringe occurs on a screen when the path length difference between waves is an integer number, like m equal 0, 1, 2, 3 times of the wavelengths. Yeah, yeah, it is a similar thing. Yeah, which means delta lambda equal m lambda. Yeah. Mm. Yeah, like we have already talked about this, and for the double slit interference, sin theta equal this one, and uh, yeah, this is the distance to the degree to the grain, and for the like this diffraction grating, yeah, this is the same. Actually, it's the same thing, and for the distance to the degree, yeah, this is the this is the equation. Actually, you also can use this equation because we have already proved that this equation also like suitable for the double silt interference if you checked what we have already learned. Does make sense? The only difference is just like yeah, you can see this one become narrower and brighter, yeah, compared with this one. Does make sense to you? Yeah. Okay. Okay, this is today's class, and like remember to finish the all the homework and the exams and the labs. Yeah, otherwise, you are difficult to get the scores. Yeah, too difficult to pass this class. Okay, bye. See you.